Greetings and welcome to the Salford Systems online series of training videos. This is a series of videos that will be covering the basics of data mining, machine learning, predictive analytics, and in particular, we'll be focusing on how to make best use of Salford predictive modeling technology. We'll be working with SPM, the Salford Predictive Modeler. This is a complete family of Salford Systems classic data mining engines, including CART, Mars, TreeNet, and Random Forest. You can work with us using SPM, which is freely downloadable from our website, from where you can get a no-cost evaluation version. If you are working with one of the earlier versions of the standalone data mining engines, such as CART, Mars, TreeNet, or Random Forest, you can still follow along, although you may not have all of the features that we're going to be discussing. In addition, you should look forward in 2012 and in other videos for detailed descriptions of what's going to be new in SPM 7.0, in particular a new generation of data mining engines and model post-processors. Today, we're going to be focusing on the SPM batteries. Batteries are a key part of the automation built into SPM. Batteries automatically generate collections of related models. They allow you to review not just one model, but a series of models laid out in the form of an experiment. This permits rapid perfection of model control parameters, and it also serves as a guide to model development because the list of batteries is a list of recommended experiments that you might want to consider as you perfect your modeling. You can use batteries to run hundreds or thousands of related models as you look for best performance or the best balance of performance and simplicity. Today, we're going to be focusing in particular on battery shave. And shortly, we're going to start up the software and show you how we actually accomplish these things using the software and the menus and the graphical user interface. Right now, I'd just like to say a few words about the thinking behind what battery shave is all about. It's one of our favorite automated model perfection tools. We start with a baseline model that might have many predictors. And when I say many, I mean perhaps several hundred. This technology may not be the best to use if you have tens of thousands. From the initial model, we can select the variable importance ranking and delete the least important variable. Keep in mind that all of our data mining engines rank the variables in order of their importance for the role that they play in the generation of that model's predictions. That list of variables is ranked with scores of importance applied to each variable, and at the bottom of that list we will discover one or possibly several that are the lowest ranked. This rank will include variables that were never used at all in the model and therefore have a zero importance. What we do with this list is we use it in order to remove the variables that are at the bottom that appear to have zero or close to zero value. Having removed those variables, we then start with a new and reduced list of predictors, and we develop a new and possibly slightly simpler model. This new model may have only one variable less than its predecessor. We build that model, and we get a new variable importance ranking. Again, we consult that variable importance list and remove the least important predictor from this new variable importance list. We then repeat this process as many times as we like. There's nothing wrong with starting with, say, 300 predictors and peeling off one at a time until nothing is left. The only thing this will cost you is the time that it takes to run such a backward stepwise elimination of variables, and perhaps you might have to set up one of these things and run it overnight. Okay, let's get started then with the Salford Predictive Modeler, which is something that you will be able to access from the Salford website. So let's get started here by going to the Open a File dialog. This is the dialog that we are always going to start with in order to begin our analyses. Here I am selecting a particular file called MJ2000. It happens to be a SAS format data file, but it could have been one of about 50 other file formats, including ASCII, for example, or Excel, or any of the other well-known statistical analysis package formats. So, having opened this data set, the thing that we'll go directly to is modeling. And in order to get started, the first thing that we have to do, and the only thing that we have to do, is indicate the dependent variable that is going to be the subject of this analysis. I'm not saying very much about the nature of this data set right now, except to tell you that it is a two-class outcome. There were goods and there were bads. The goods were recorded as ones and the bads were recorded as twos. We have, in addition, 25 predictors that are available to us, and we're not going to say anything in detail about those predictors either. We're focusing here on just our methodology. By default, all of these predictors are in the model, but let's go ahead and make that explicit over here. And the only other thing we're going to do to get started is when I go to the testing tab of the model setup dialog, I want to select a train test methodology with 50% of the data being held back for testing. I'm using the CART data mining engine. There are a bunch of others that I could have used instead, but let's stick with CART for right now, and let's hit the start button. Okay, so our analysis is complete, and what do we see here? We see that on the test set, which was a genuine set of data which was not used to build the model, was half the data approximately. We have an ROC of 0.79. If you're not familiar with that, we'll look at some other performance measures, but that performance would be considered excellent for this type of problem. If we look at the summary reports, what do we see here? If we go to the prediction success or the classification accuracy, we go to the test data, and what we can see here is that on the class 1s, which are the goods, on the test data we're 75% correct, and on the class 2, which are the bads, we're 77% correct. So the overall correct percent is a little over 76%. Okay, not so bad. As we said before, when we want to start the shaving process, if we were doing this manually, we would look at the variable importance ranking, focus on the least important variables, and remove one or more of those. Let's see if there are any with zero importance. And it turns out, yes, there was one variable with zero importance, so that's going to come off automatically as well in this process. But we don't want to do this manually, so let's go back to the modeling dialog, and let's go to the battery tab, and this is where we're going to set up our modeling process. Okay, so we can see here in the battery window that we have a large variety of battery types, and eventually we're going to work through all of these in different videos. Today, let's just select shaving, add that to the batteries that we're going to run now, and let's set up some of the controls that we have available to us. So the first item is how many variables to shave in each one of the cycles. So if we're going to follow the musical chairs paradigm, then we're going to lose one variable in every cycle. This option here, shave from where, well, in this case, we are going to be removing the least important variable when we remove. We could also be removing the most important variable, but that's another topic for another video session. And how many steps shall we take? Well, over here, I want to set this to 20. We could set it to as high as 25 if we wanted to shave off all the variables. Well, let's just hit the start button and see what happens. The first thing to point out is that we're going to have to build 20 different models in order to do these 20 steps of backshaving. If you had, therefore, 300 variables, you're going to have to allow enough time to build all of those models. And how long the whole process will take will obviously depend on the number of records that you have in your data set, the number of variables that you want to process through, and the speed of the processor that you're working with. In this particular example, I happen to know that this will execute relatively quickly, so I haven't bothered to try to pause the recording and come back when it's done because we're already done. Okay, so once we complete a battery, we always get a battery summary that looks like the one that we have over here. What it shows us by default is some kind of performance on test data. And this graph over here shows the performance of all of the models that we developed. And we're showing the relative error on the y-axis here. So the higher the curve location, the worse the performance of the model. On the x-axis, what we are listing in order are the variables as they were removed during the backward shaving process. And if you remember, when we developed one model manually, this variable over here, GEN, was in fact the least important variable. So this is exactly what we would expect. It would be the first one that would be shaved off. The initial model that was built removes nothing. So it is actually described as x underscore none, leave the model alone. Then we get x underscore gen, remove the gen variable. Once a variable is gone, it's gone forever. Next we remove this variable e, and so forth. So what's interesting about this particular curve? Well, what's remarkable about the curve is that as I start removing variables, initially it costs us nothing. The model performance doesn't get any worse at all, at least within the accuracy that we can see from this graph. Then it appears to get very slightly worse, and then there are a number of steps in which the general trend is that the model is improving with a little bump over here. So until we get to the removal of this variable CR, we've been on a downward trend in terms of predictive error, and therefore an improving trend in terms of the performance of the model. The pattern that we see here, that is, that a model actually gets better as we remove some of the available predictors and predictors that were actually used, is a pattern that has been well known to be relevant, especially to decision trees. If we can somehow get rid of the variables that really don't add much to the performance of the model, then we're very likely to get an overall better model. This is a topic that we'll also discuss more in another video. Okay, so now that we observe the downward sloping trend, what happens after that? Well, what we see is that the error curve starts to rise, and not only just a little bit, but it increases quite a bit and at a very rapid pace. What does that tell us? It tells us that we have shaved, at this point, we're shaving too far. That is, we have removed the variables that we can live without. but we're now starting to remove the variables that are important and critical to model performance, and so we don't want to go that far. If we click on the Show Minimum Error button over here, we get tree number 19 out of the models that we built. The 19th is the one that shows the best performance, and it has 6 predictors in it. Let's go ahead and actually double click on that line and look at what happens. The model that corresponds to that particular shaved set of predictors comes up, and we can compare it directly with the initial model, which is the one that we started with. So let's position these on the screen so that they're easier to see. Side by side, I guess we'll do, or sort of side by side. And let's see what comes out of them. This was the first one we ran. This measure of performance, ROC on test data, 0.7903, is a little bit worse than the model that we get after the shaving process. It has an ROC of approximately 0.81. So that's actually a fairly big difference in terms of this type of model. And so it's worth paying attention to. But what's more important than anything else is that we are getting equal or better performance on test data with many fewer predictors, only 6 instead of 25. So there's only 6 variables that are really necessary in order to get us this level of performance. Also interesting is the fact that the optimal cart tree in the shaved version has 18 terminal nodes, whereas when we started, in which we had too many variables, we have 36 terminal nodes. Again, this is not a surprise. If we have variables that are really not contributing much in retrospect from the perspective of the whole tree, but which happen to get involved in the analysis along the way, then the tree actually has to do more work because some of the splits weren't particularly as good as they could have been if we had worked with a more streamlined set of predictors. So the new model will be more streamlined and also more accurate, and that is benefiting on all possible dimensions.